Bismillahirrahmanirrahim. Hello students, how are you? I hope you are all fine. Today we have this AS Physics 9702 chapter number 4, Forces, Density and Pressure. The last lecture we discussed was basic concepts of the your chapter, yani forces. Today we are going to discuss the equilibrium of forces and the related topics. First of all, what is the equilibrium? So this is very important to understand that like rest or motion, here we have another state of the body which is termed as the equilibrium. And how we can define this equilibrium? So simply when a body is at rest or moving with uniform velocity, the body is said to be in equilibrium. Yani a body will be in equilibrium when the body is moving with uniform velocity or at rest. So there are two possibilities, and like if a body is at complete rest, then it's a complete equilibrium. But when a body is moving, so you can say that the body has the translatory motion, but still the result or the resultant force or forces acting on the body are balancing the effect of each other. So there is no acceleration, and when there is no acceleration, the body is moving with uniform velocity, and this state of motion is termed as the equilibrium. So this is what we have. Then without going into detail of this you can say topic, just want to tell you that the equilibrium may be the equilibrium, translatory equilibrium, or rotational equilibrium. Rotational equilibrium. So these are two possible equilibriums. Like suppose if you are considering a bicycle which is standing on, say here you have the situation. I'm not good in drawing, but just trying to give you the idea that if you have a bicycle here and this bicycle is standing on the stand, then what is the possibility? The possibility is that you have the wheel which is rotating, and you can rotate the wheel when the bicycle is standing on the stand. But when you have the wheel, you can see that the wheel is rotating. Over here you can say that there is no translatory motion, yani the body at rest as far as the translatory situation is concerned, and the body is not moving in this direction, but still you can see that the wheels are rotating. So this is what we have as far as the situation of translatory equilibrium, when the body is at rest. Or even if the body, as I said earlier, the body is moving with uniform velocity, of course the wheels are rotating, and what is happening, the situation is that you have the translatory motion as well as you have the rotational motion. So you can say that the body will be only in equilibrium if the this condition is applying, moving with uniform velocity. So as I said that excuse me, you need not to go into details of these things, but just to give you an idea that we have a possible translatory equilibrium or rotational equilibrium. We are moving towards the topic which we have in our syllabus, which is the principle of moment. Principle of moment is basically a topic which you have studied in your O level or IGCSE as well. And here basically when we will talk about the rotational motion, then we can talk about the principle of moment. So what is the principle or the statement of the principle? For a body in rotational equilibrium, the clockwise moment is always equal to the anti-clockwise moment. So this is the principle of moment, yani clockwise moment is equal to the anti-clockwise moment, and at that time you will say that the body will be in rotational equilibrium. Conditions we will inshallah study later on, but for the time being this is very simple sort of situation, that if you have here, as we have considered a rod or a meter rule, and this meter rule is you can say supported at this point. So this is the pivot at which you can rotate the scale or ruler, and of course here you have one weight W1 on left side and W2 or right side. So for W1 the perpendicular distance is D1, and for W2 the perpendicular distance is D2. So if you will see that the rotation or because of W1, or the moment because of the W1 is nothing but W1 D1, and here you can see that this is nothing but the anti-clockwise rotation. On the other hand, if you will consider W2, then you will see that is a clockwise rotation, and here simple moment is nothing but your W2D2. So this is what we have as far as the situation is concerned here in case of a ruler. In the last discussion, actually, we have discussed one thing, that the body is rigid body, and we have considered and discussed the center of gravity as well. Just to tell you one thing, that if you are talking about here, like in this case, we have a uniform rule or ruler, then remember this thing, that in case of uniform ruler or bodies, like if you have a suppose a telephone pole, or if you have anything like this, then you have to find out the center of gravity. Like in this case, the center of gravity will be at the geometrical center of the ruler. Then you will have the case of uniform ruler, but or uniform body, yani the mass is uniformly distributed over the ruler. But if you have a pole like telephone pole, suppose, as I just gave you an example here, this is the telephone pole suppose, then what will happen, this, remember this point, that the center of gravity will always be towards the thicker side, and this is very logical. I will come back to this again, but here for this example which we are discussing, as far as the principle of moment is concerned, W2 D2 is the clockwise moment, and W1 D1 is anti-clockwise moment. When the body is in rotational equilibrium, this principle must be followed. Here, as I said earlier, that this is very important to consider the point of support or pivot, but the position of the pivot is not important. The moments can be taken about any point. Yani, you can consider any point on the scale, and instead of suppose this position, you can say that the support is somewhere here. Then if you are using this point for the support, what will happen, both these weights you can see are on one side. So it means that if you want to balance this, yani both of these given weights here are giving you the clockwise moment. So if you want to get an anti-clockwise moment to balance this situation, then you have to hang a weight like W3, and this W3 with this distance, say D3, will be, you can say, your counter, you can say the moment, and this is your anti-clockwise moment. Both of these W1 and W2 are giving you in this situation the anti-clockwise, you can say clockwise moment, and here you have the anti-clockwise moment. So you can balance this, you can say ruler, but pivot is not important. This is very important point. If even if you are using only W1, that instead of this position, you can say that I am not using this weight here, this is the point, and here we have suppose W1, and here we have W2. Then you can say and see that W2 multiply by this distance. In this case, we can consider this distance is D2. So W2 multiply by this distance will be equal to W1 multiply by D1. We can consider this as D1. So here you have to consider a situation like this, that as you can see that W1 has you can say perpendicular distance D2, which is very big as compared to the D1. So the weight W2 will be very small as compared to W1. Here I can show you one simple say sort of animation, and here suppose you have this animation, which is I think very helpful to understand the whole situation. Here you have a ruler, and of course you can mention that what is the position of your weight or whatever you are using here. Suppose if you are keeping your weight at 1, so of course you can see that the ruler will topple on one side. But if you want to balance this, yani basically this W1 is giving you the anti-clockwise rotation. But if you want to balance this anti-clockwise rotation, you have to use the same weight at the same length. So when you will use 15 kg at 1, this will give you the clockwise moment, and then you can see that the whole situation will be in balance. But instead of suppose this 15, you are only using 5, then you have to consider one thing. 15 here you have the of course on the left hand side I'm talking about. So from the pivot to your value of 1 meter or whatever, here you have of course not 1 meter, the meter rule you have. So but the thing is that for 1 suppose centimeter or 1 whatever the unit, multiply by 15 will give you 15. So you have to balance this 15. Like suppose if you have this 5 and you are keeping this thing suppose somewhere here, you can see that the thing is happening. But if you are using this 10 at 1.5, then what will be the situation? 10 multiplied by 1.5 will give you 15 again. So you can see here that the weights are different, but the perpendicular distance is also different. Than for a smaller mass, your perpendicular distance on the right hand side is 1.5 and you are getting moment as 15. Yani 15 is the moment on your right hand side, which is giving you the clockwise rotation, and 15 multiplied by 1 is on the left hand side, which is giving you the anti-clockwise moment, and you can see that the whole situation is balanced. So only by using a longer you can say the perpendicular distance, you are getting the same effect. The moment is same. Now if suppose you have another situation, like suppose 15 multiplied by 2 you have, so this is 30 and you can see that is toppled. So what you can say, what you can do, here you are using now weight suppose 20 kg. So here you have 15 multiplied by 2 which is 30. So what will be the situation of 30? When you are using suppose weight 20, where you can use this 20 here, 1.5 multiply by 20, what is the result? Simply you can say 1.5, when we are multiplying 1.5 by 20, we are getting again the same value as we have on the other side. So 15 multiplied by 2 is 30 and 20 multiplied by 1.5 is also 30. So you can see that the situation is again balanced. So the counterclockwise and clockwise moments are equal to each other. So the whole situation is balanced. Here you can show the forces, and you can see that of course the force of 20 kg or force because of the 20 kg is greater. The force because of 15 kg is lesser, but on the other hand for 20 kg the moment arm is 1.5, and over here we have on the other side we have moment arm as 2 for your 15 kg. I think it's clear. So this is what we have. Here you have the force. Here of course this is the level situation, yani the ruler is balanced. And of course if you will do it right like this, so this is not a balanced situation. So when you will use the weight, you have to consider that what is the weight on the other side or what is the force on the other side, and the perpendicular distance will change accordingly. So you have different options, like suppose a man, he is standing suppose somewhere here 0.75. So when you will multiply by this distance is 80 multiplied by distance is 0.75. So the result is 60. So what you can say, what you can do, if you have this person and you are using suppose this person is sitting somewhere here, this person is the boy is sitting somewhere here suppose, then you can see that nothing is happening. But what you can do, what you can say, that now if you want to balance this, we have to do something. Like suppose 20 multiplied by 2 is giving us 40. So if you want to get 40, you have to move the position of the person somewhere here. So when you will change the position of the person from 0.75 to 0.5, then 80 multiplied by 0.5 will give you the moment of 40 Newton meter. And on the other hand, of course, the boy is also giving you 20 multiplied by 2, 20 multiplied by 2, and you can see that you are getting the same moment on the other side as well. So the whole situation is balanced. I think it's clear. Here we have another, you can say, like animation, and in this animation you can say and see that we are using a ruler with holes in it, and particularly when you will do the experiment in your lab, this type of situation you have to deal with. Here you have weights. So if you are hanging weight at 5, so what is happening? Of course, you can see that the clockwise moment is 5 multiplied by 5, which is 25. So how you can get this 25? So suppose you are using here 6, nothing is happening. You are using here 4, you are using here. So what is happening? 2 multiplied by 3 and 2 multiplied by 4. So 2 multiplied by 3 6, 2 multiplied by 4 8, and on the other side 2 multiplied by 6 was giving you the more, you can say, reading as required. So what you can say, that now I am using here something like this, so it's more. So it's still what you can do, you can change the position of this thing, and suppose here you are, nothing is happening. Here you can say nothing is happening. You can use this weight somewhere here, suppose, then nothing is happening. Then what you can say, you are using this weight, is more than required now. So if you will change the position, so what is required? 1 and 2 3, 3 and 1 4, 4 and 2 5. So what you have to do, instead of this position, you can say that we can change the position somewhere here, and when you will change the position, you can say that now I am using this position, it's more again. So by hit and trial method, you can simply say that there will be a point at which the weight will balance the other part. So we are basically increasing. So what we have to do, suppose we have to decrease something like here. So again, you are using this value. So in this way, you can say now it's balanced. So now check. Here the counterclockwise is what? 1, 2, 3, 4, 5. 5 weights hanging at point 2. So 5 multiplied by 2 is 10. And on the other side, 2 and 1, yani 3, are hanging at 5. So 3 multiplied by 5 is 15. This is I am talking about on the left hand side. So 15 plus 10 is 25, which is balancing the effect on the other side. The weight you have is 5 and is hanging at 0.5. So the distance for 5 is 5, and this is giving you the clockwise rotation. And what we did here, basically, again we can do it, and of course what we are getting here, 25. On the other side we have balance by different weights and different positions, and we are getting the same result. Same thing which we can do here, like suppose we are using, this is 7 multiplied by 5, this is 7 multiplied by 5 means 35. So what you have to do now, again you have to use another weight somewhere here, suppose. So you can say that it's unbalanced. So when you will remove this weight, you can see that the situation is unbalanced. So slowly and gradually you will get something like this. It is still unbalanced. So what you can do, you can use this weight, suppose somewhere here. Let's see. So now you can see the whole thing is balanced. So what you have to do, On the right hand side, you have only one force of 7 Newton. 7 Newton is multiplying by your moment arm, which is 5, yani perpendicular distance from the pivot, and it is 25. On the other side, you have 4 forces, 1 and 1, 2, 3, 4, 5, 6, and 2 and 2. So you have these 4 forces on the left hand side, and for each of these forces you have different moment arms, and when you will multiply the moment arms with the respective weights or forces, you will get a situation which is giving you the balance situation on the other side. So you can do your own calculation. So this is what we have as far as the principle of moment is concerned. I hope the point is clear now. I'm coming back to this discussion here, and again, just to complete this part, as I was telling you that if you have a uniform ruler, then the center of gravity will be at the center. It means that if you have a situation like this, then you are hanging a weight here W2, you are hanging another weight here W1, but the weight of your scale is also acting downward at this point. So when you will consider the situation of weights or forces, in this case you have to consider the weight of your ruler as well. Yani simply if I want to write an equation for the balance situation of your ruler, then what will be the situation here? Simply if you want to write an equation, what you can write? Simply you can say that W1 multiply by D1 is equal to what? You have here W2 multiply by D2, but there is another force which is weight of the ruler itself, and of course here this is the distance for this particular weight. So you can write this is the dw or dr, yani this dr is showing you the distance of your pivot and your weight. So perpendicular distance is dr. So this will be the equation this time. So be careful. On the other hand, if you have a situation like this, as I have drawn here an example, so in this case what will happen, you can see that the center of gravity is lying on the left hand side, yani thicker part, and simply you can say that if you will consider this whole part has a weight and this part has a weight. So what will happen? If you are considering the weight of this part as W1, and you are not hanging anything, but you are just considering that here you have the weight of scale on the left hand side, and here you have weight of the scale on the right hand side, and one has a thicker part, of course, another has a thinner part. So for this part, which is the comparatively thinner part, of course the weight will be less, and you can see for that this whole weight, the moment arm or perpendicular distance, like suppose if you are considering this W2, will be greater as compared to this weight. Remember this thing that I am just taking the weight from the corner basically. So remember this thing, I am just drawing W2 somewhere here, but if you are you can say having any sort of confusion, you can say that instead of these arrows we can draw arrows somewhere here, meaning at this point this is W1 and this point is W2. So basically these are the weights of the ruler itself. So as you can see that the weight of the thicker part is greater than the weight of the thinner side. So W1 is greater than W2. So what will happen? D1 must be smaller than D2, and actually this condition smaller than or greater than we have just discussed in the animations as well. So I hope this point is clear now, and you know that what is this thing? This is non-uniform. non-uniform ruler or whatever. I hope this point is clear. So if you are considering the equilibrium and the principle of equilibrium, so these are the you can say points which we have to remember. As you can see that I have already written these points, so these are the notes you can use. If you are new on my channel, so subscribe this channel, press the bell icon so you can get the new uploaded videos and you can complete your course with me. And of course, if you will share this channel with your friends and the contacts, then these students can also get the benefit of this channel. So, and of course, if you have any problems, just tell me your problems in comments, and I will try to give answers. In description, you will see my WhatsApp number, and if you have any problems, you can contact me directly as well. Now moving to the another point, which is the conditions of equilibrium. Here we are talking about the conditions, and like suppose we are considering this you can say body, and first of all this, let me tell you that we are talking about the conditions of equilibrium. So two conditions for equilibrium for a rigid body we have. First condition, this is the condition where we will talk about the forces, and for the second condition we will go for the moments or torques. So these are two conditions, but one by one we will discuss these things. Let me consider here a body like this, you can see, and you can also see that there are forces F1, F2, F3 and F4 acting on this body. Here forces F1 and F2 are acting along x-axis, while the F3 and F4 forces are acting along y-axis. So what is the situation here? If you have the situation like this, that F1 and F2 are equal to each other, then the difference of these two forces will be zero. The difference of these two things is zero, means the resultant force along x-axis will be zero. So be careful when we need an equilibrium. This is the first part of first condition, that the forces along x-axis must be such that they are balancing the effect of each other, and the resultant force along x-axis must be zero. And how you are writing this fact? Summation fx is equal to 0. So what we are saying, that when we are going to add these forces, then in result of these two forces we are getting 0. So summation fx is equal to 0 means that all the forces acting along x-axis is equal to the sum of these two forces will be 0. And here, like suppose we have written in this way, that F1 plus minus F2, yani one force is in negative, another force in the positive direction, and the result, of course, if the forces are equal and opposite in direction, then what will be the situation? The resultant force will be 0. So as I said, this part will be the first part of the first condition of equilibrium. The second part is about the y-axis, any forces along y-axis. So as we have just discussed that forces F1, F2 must be equal to each other and opposite in direction. So same is the case if you are considering forces F3 and F4. These forces are equal and opposite. If these forces are equal and opposite, then you can write it like this. And of course the resultant, again as we had just discussed in case of x-axis, the same will be the situation of the forces along y-axis, and summation Fy is equal to 0 is showing you that all the forces acting along y-axis must be 0. And if you have these two conditions, simply you can write that these two conditions are leading towards this fact, that the situation here is simply summation F is equal to 0, yani all the forces acting along x-axis and y-axis, or simply you can say all the forces acting on a body must be equal to 0. And what we have written here, so this is the first condition. the vector sum of all the forces on a rigid body must be 0. You can recall that what is the rigid body, which is the has a structure, fixed is a structure, and the forces cannot change the shape of the body, so the body will be the rigid body. As I said, that if you want to get the detail of this rigid body and all you can say related topics, go back to the first lecture of this chapter, and of course you have to you can say go through that lecture as well, so you will get a better idea of this chapter. So what we are talking about, the first condition of equilibrium, the vector sum of all the forces of the rigid body must be 0, and mathematically what we are writing here, we have summation F is equal to 0, means the forces along x-axis is equal to 0, the forces along y-axis is 0, and of course what is happening overall when the forces or the resultant of the all the forces will be 0, so the body will be in equilibrium. So this is very, very important. So here we have this very important condition that the body will be in translational equilibrium. As you can see that the body is not moving here and not moving on the other side. But if you will change the position, like suppose you have the first condition is okay, but instead of the forces you have in this position, then what will happen? These forces, of course, cannot take the body along x-axis or y-axis, but these forces can give you a rotation. So it means that the body is not in complete equilibrium, it still has a rotation. So if you want to get the rotational equilibrium as well, so you have to go to the second condition of equilibrium. But before going to the second condition of equilibrium, we can take examples of the forces in equilibrium. Like suppose if you have this situation that you have two forces in opposite direction, yani making an angle of 180 degree, forces are equal. So what will be the situation? Simple. Here what we are writing, they are equal and opposite along the x-axis. So simple thing is that, as we have already discussed, that the body will be in equilibrium, at least along x-axis there will be no translatory motion or motion in a line. Same, of course, you can write for the y-axis if you have forces like suppose this, as we have already discussed. So two forces in opposite direction along y-axis will give you summation Fy is equal to 0, and this will be another possibility. If you have forces like this, like suppose you have three forces, then what will be the situation? You have three forces F1, F2 and F3. F1, F2 and F3 making of course angles with each other. So here you can do something like this. They will form a closed triangle. Yani what we can say, like suppose if you will take this force somewhere here and you have another force like here, and this force you can draw parallel to somewhere here, then this will be a closed triangle. You can see what I did. I have taken this force F2 backward. I have drawn this F3 parallel to this one. This is F3. So when you will do like this, you will get a closed triangle like this, F1, F2 and F3. So you can see that F1 is downward. So you have drawn a downward force F1. You can see the F2 is towards right, you can say. So here you have F2 and F3 is towards left. So when you will draw a third force, you can see that the triangle is closed, and it means that there is no resultant force. Fx and Fy are 0, means that suppose what we can do here, another possibility is we can do like this as well. I can draw it like this. What you can do, here you have a situation. Here you have angle theta. Suppose this is theta 2, and here you have an angle, say this is theta 1. So this is actually another way to describe the same thing. One thing which I have just discussed is making a triangle, a closed triangle. Another possibility is that what we can do, what we can write, that the forces, here we have, this is your F2y, here you have F1 x, F2x. This is your F3x. Here you have your F3Y. So simply what you can say and see that F3Y upward force, F2Y upward force. So you are going to add these two forces. But what will be the situation of the force F1? So simply you can say that F1 is equal to these two upward forces. Yani simply you can say the upward force or forces must be equal to the downward force or forces. Downward force or forces. So when you will have this condition, again here as I said that very simply you can also mention here that this F2x and F3x, you can see that they are in opposite direction. F2x is here, F3x is here. So simply you can write that to get the balance situation, a complete balance situation, here we have F2x must be equal to F3x. As far as the x-axis is concerned, there is no role of your F1 because this is only downward force. But when you will talk about the y-axis, any downward situation, you have to consider all the downward forces or upward forces. So upward forces, as I mentioned, are your F2y and F3y, and downward force your F1. So this is another possibility, as I have already mentioned here. We can use the rectangular components method to solve these problems as well. Got it? So this is what we have. Again, we can go to the animation side, and like here you have the situation of forces in equilibrium. You can very simply see that here we have a free body diagram. Point mass means that we are considering a body at this point, and the forces F2, F1 and F3 are acting on these this body. So here what we can say that we can also show the angles. So here we have the possibility, but if we are not showing the angle, we can change the position, and you can see that here we have the situation of the balance body. Yani body is in equilibrium. You have forces F1 which is 5.3. You have force F2 which is 5.8. Downward force is 8.6. And when you will draw the you can say a vector triangle, here you will have a situation like this, that you have drawn this vector, then F2, as you know that you are following the hat to tail rule, of course, and you have F3 as well. But here, as you can see, that the point from where you are starting is the point of termination as well. Then this vector, then this vector, and then this vector is coming back to the point of start, you can say, and it means that there is no resultant force and the body is in equilibrium. And if you want to show the you can say the angles, very simply you can show the angles as well. So you can say and see that what are the angles here. So they are showing you here these angles as well. So here very simply, as you can see, that you are showing the forces, and you can of course change the force, and you can change the situation here. So angles between like F1 and F2 is F theta 1 2, which is 101. So here you can see that what will be the situation of this angle. Similarly, F13 is 129.7. But of course, when you will draw the triangle, you have to be careful that this angle or which angle you have to consider where. So this is very, very important, that when you are going to draw the triangle, you have to consider, like suppose here you have 101 between F1 and F2. So where is F1 and F2? This is your F1 and this is your F2. So this is the angle. So you can see here that this is 78.3. So how you are getting this 78.3? Because if you will extend this force, this angle between your F1 and F2 will be 101.7. So the, you can say, inner angle of the triangle will be only 78.3. And of course same is the description of your 129.7 and 128.7. So when you will consider all these forces and angles, you have to consider that when you are drawing a triangle, what will be the situation of the triangle. So this is very, very important to understand that where we are and how we can draw these triangles. As I said that you can change the position, but this will be the result of the you can say, or the resultant triangle, respective triangle. Free body diagram means that where you are not showing the actual body, only you are just using a point mass or a point to represent the body, but this overall diagram is termed as the free body diagram. And of course you have to draw the respective vector triangle. And as I said that the only point you have to consider is that when we are drawing a vector triangle, it will be a closed triangle, and it's coming back to the same point where we are starting. It shows that there is no resultant force. So this is what we have as far as this you can say animation is concerned. I hope this point is also clear. Now move to another situation, and this is the second condition of equilibrium. As I said earlier, that if you are considering this body having these forces, and if you will consider the fx and fy, is very simple. But even if you are changing the position of your f1 and f2, the same condition is applicable. But over here you can see that you can get a rotation because of the change of position, because here you will have a particular distance for these two forces. Similarly, if you are taking these f3 and f4 somewhere here, these are the perpendicular distances. So if you want to get the rotational equilibrium, this must be the condition you have to follow. The vector sum of all the external moments or torques acting on a rigid body must be 0. So I have already explained this thing, that anti-clockwise torque must be equal to clockwise torque. As you can see here, that like this F1 and F2 are giving you the rotation, and of course F3 and F4 also giving you the rotation. So both of the or all of these forces are giving you the rotation in the same direction. So the body is not in equilibrium, the body is rotating clockwise. But if you want to get a complete you can say sort of equilibrium, then as I said that what you have to do, you have to change the position of suppose these forces f3 and f4. So when you will change the position, what you are getting, you can simply say that now f3 and f4 giving you another rotation. And what is the rotation now? We can use another color here, suppose this color. So you can say and see that these three forces, yani F3 and F4 forces, not three, only two forces, are giving you the rotation like this. Now the rotation is like this, yani here you have anti-clockwise rotation. So your F1 and F3 giving you the clockwise rotation like this, and your other forces, yani F3 and F4, are giving you anti-clockwise rotation. So the moment, clockwise moment is equal to the anti-clockwise moment, and then you can say that we have a complete rotational equilibrium. So to get the complete rotational equilibrium, you have to have this condition. Any second condition of equilibrium must be applied or applicable in case where you have a rotational equilibrium. And the overall, what you can write, summation tau is equal to 0. This is tau. This is tau. The symbol is tau. T-A-U, tau. So this is for the torque or a couple. Particularly in our syllabus, basically in our syllabus they have mentioned that if we have a one force only, then the term we are using is moment, and when we have two forces, the term is the torque. Because the two forces, we have used the term couple of forces. As I said, go for the first chapter, for first lecture of this chapter, and you can get the idea that what is the situation of the moment and torque of a couple. Excuse me. So this is what we have as far as the you can say the rotational situation is concerned. Here I just want to mention another animation, and like suppose you have a situation like this. Here you can see that we are talking about a sort of bar or a bracket which is you can say fixed in or with a wall. And what will be the situation here? You have the hinge, the contact force which is acting in this way, the weight of the body, whether it's a you can say rod or bracket or whatever, is acting downward, and here you have the tension. If you have a rope or a cord which is balancing the whole thing. So what you can say that if we have this situation, then the body is in equilibrium. But if the you can say the force is somewhere here, you may have a situation. If you will consider again, as I said earlier, that if all these forces are passing through the same point, then the body will be equilibrium. Yani, what is the situation? All these forces passing through the same point means they will make a closed triangle. When you will draw these three forces and they are giving you a complete you can say a closed triangle, then the body will be in equilibrium. Over here we are talking about a uniform weight, yani the body is uniform. So the situation is simple. Contact force is acting along x-axis, and when you will resolve the forces, any tension, you will get Ty and Tx. So you can simply say and see that Ty is balancing your weight W, and your Tx is balancing the force Cx, which is the contact force. So again, as I said, that you can talk about the first condition of equilibrium in this way, that the force Cx is balanced by force Tx, and the force Ty is balancing the force W. So this is the first condition of equilibrium you are applying. But of course you can apply the second condition of equilibrium here as well, and this will be very simple, because if this is the point, suppose Cy is the point or hinge is the point which is your pivot. So for weight and this Ty, the moments will be same, but whatever this Ty, this is very important. This is important, that what is this Ty. So these are you can say sort of problems you will face in this particular chapter, and of course you can solve these very simply. So this is what we have as far as the situation of your second condition and first condition is concerned. I will show you inshallah the other animations as well, but here we have to quickly talk about two small things. Like, one is the concurrent forces. What are the concurrent forces? So simply you can define that these are the forces whose lines of action pass through a single common point. So as I said, that if you have a situation like this, that you have different forces and these forces are passing through the same point, that you can say that all these forces will balance the effect of each other. Here we can explain further in this way that to determine whether concurrent forces acting on a rigid body has a translational or rotational equilibrium, we have to check whether the condition 1 is satisfied. Then first of all you will check that whether the first condition is applicable or not, or is satisfied. Then the summation F is equal to 0. If this will be the situation, if the vectors or the resultant is 0, the vector sum of all the moments acting on the body must be 0. Then the second condition is also you can say applicable, and you can write here that condition 2 is presumed to hold. Yani if all these forces are passing through the same point, then the automatic situation is that the second condition will also be applicable, because there will not be any perpendicular distance from the pivot. Like in this case, I am just showing you this animation, and here you can see that we have a situation like this, that we have forces A, B, C, and all these forces are passing through the same point. So this body will be in equilibrium. But if suppose you will consider this body somewhere, this force somewhere here, then what will be the situation? You have a net force, and this net force will not, you can say, allow to body to have a sort of equilibrium, because this force can rotate, or this force can give you the translatory as well as the rotational motion. And here you can see that if you have suppose this as a center, then what will happen? The resultant force will give you the rotational effect as well. But when all these forces are passing through the same point, then you can say that all the forces are passing through the same point means no rotational effect you can produce. As I said that in the first lecture, I have explained this point as well, that if you have, like suppose you have this situation, again you can see that this is the net force acting on the body, and whenever you will have a net force, the body will not be in equilibrium. So if you want to have the situation of equilibrium, you have to consider this situation as well, that whatever the forces are given, they must pass through the same point. So if they are not passing through the same point, of course you can say that you have the resultant force. And when you have the resultant force, what will be the situation? The ultimate situation is that you will have rotation. So this is very, very important. I hope this point is also clear. And of course we have other animations as well, but just to avoid the length of the lecture, I'm not showing you more animations, but I think the points what I want to make here is clear, or are clear. Like here you can see a few examples of concurrent forces. Like you have a situation of say a flagpole, the weight is acting downward here, the tension is here, and the reaction of the wall is here. So if all these forces are passing through the same point, as you can see, then the body will be in equilibrium. But if either of this force is not passing through the you can say same point, like suppose the body is somewhere here, or the weight is acting somewhere here, then this force will give you a rotational effect, and of course the body will not be in equilibrium. Same is the case here. If you have say a sort of ladder lying on a smooth surface, then here you have the reaction force from the wall, here you have the rough surface, earth suppose, or ground, then the reaction is coming like this, and of course the weight is here acting downward. And what you have to do, what you have to check, whether all these forces, any weight, reaction, and this reaction, these the forces, if passing through the same point like this, then the body, yani this ladder, will be in equilibrium. Any force, whether it's weight, or this reaction from the surface or the ground, or this reaction from the wall, is you can say different, or the line of action is different, then the body will not be in equilibrium. So this is what we have as far as this situation is concerned. Okay, and I have actually already discussed this law of triangle. What is the law of triangle? Particularly if you want to state this law of triangle, you can write in this way, that when three sides of a closed triangle represents three coplanar forces, coplanar and in a same plane, acting on a body, then the body will be in equilibrium. So this is very, very important to understand, as we have already discussed that here we have force F1, F2 and F3, and they are making a closed triangle, then simply we can say that we have a situation of the equilibrium. So if you want to get a sort of a technique, you can say, to solve problems based on your moment and talk and all these, so this is one of the very important technique here we can use. And as we have already discussed, that the vector sum of all these forces must be equal to 0. Like here you can say that F1 plus F2 must be equal to F3. Yani if suppose you can consider the opposite situation, like suppose F3 is in this direction, then this F3 will be the resultant force. So this resultant force is not required for a balanced situation or equilibrium situation. So what we have to do, we have to consider the negative F3, which is something like this. So here when you will add all these, you will get the result as 0. And of course, if you have these angles given in any case, as I have already shown you in the animation, so you can use the sine law, and of course the sine law you have studied in, I think, O level and IGCSE as well. So this is something which is important. uh, like this you can use these possibilities or combinations. Yani f1 f2 or sine theta is given, then you can find out sine theta 2, sin theta 1, sin theta 2, f2 is given, so you can find out f1 and so on. Yani like suppose you can consider this side of the equation, so f2 is given, theta 2 is given, theta 3 is given, you can find out f3. So in this way you can use the sine law as well. So this is very, very important, and I hope today what we have discussed, you have a good understanding. And of course, if you are not getting in one sitting, so I think you must revise this lecture again and again 2 or 3 times. But I think this will be very useful with the animation and everything, and hope you will get the idea of the coplanar forces and the concurrent forces, and the use of the first and second condition of equilibrium, what are the situation of your principle of moment. So everything we have discussed here, and this is something which is very, very important to understand. And as I said, that if you can understand the topic, the problem solving will not be difficult. Inshallah, I will give you one or two at least problems as well in the next lecture. I will upload 2 or 3 problems where you can understand whatever we have discussed up to this point. So again, I can just tell you that if you are new on the channel, you have to subscribe this channel so you can get all new uploaded lectures, and these lectures will help you to develop your concepts. And of course, ultimately we are going to solve the problem. So if you cannot understand the topic, you cannot solve the problem, because even 100 problems you will solve, 101 problem, and then again you will stuck because you are just holding the finger of a person. So this is not a good situation. I always say that a good teacher is a person who will make his or her students independent of himself or herself. So this is the target. So if you are working independently, I think this will be my success. So be happy and energetic. This is very, very important. Energy is very important, because if you are not energetic, you are not acting according to the time management and energy management, you cannot get anything. So see you in the next lecture, inshallah. Till then, Allah Hafiz. Take care.